Well, welcome everybody to Geohug, and I'm so excited. We have Asmita Mahanta joining us today. So, Asmita has more than 28 years of experience in exploration and mining. She currently holds the position of Global Practice Lead of Geophysics at BHP. And she's worked in both greenfield and brownfield exploration and mining across various commodities, including base metals, diamonds, and iron ore. So, expertise lies in connecting resource knowledge to business decisions and use of innovation and technology to mitigate risk, uplift productivity, and unlocking resource value. So, with her expertise, it is going to be brilliant learning from her today on geophysics in the mining value chain. So, thank you so much, Azita, for joining. It's awesome having you here today.
Thanks, Jess. It's a pleasure to be here today.
Oh, love it. I was really curious what got you into geology and geophysics to begin with.
Well, I grew up in Assam. Assam is a small state in northeast of India, and it is famous for three things: tea, one-horn rhino, and oil.
Oh, there you go.
India's first oil well was actually drilled in Assam, a place called Digboi. And there is a fascinating story. I'll tell you the story because you shared your story with me. And it's the story. There are different versions there, but I like the version about this Canadian engineer who was building railways um, around that area. And he saw these elephants. The elephants were carrying timber. And he saw these elephants' legs were stained with oil stains. So he just stopped his people and he said, dig, boy, dig. And from that, the name of the town became Digboy.
Oh,
So yeah, there you go. And the place I grew up, it's not far from Digboy. So I have actually grew up seeing those oil tankers passing through the highway, and I did hear about geophysicists, geologists, and chemical engineers. But I can't tell you that I actually grew up dreaming to be a geophysicist. I actually did study physics, but very quickly I realized that theoretical physics is not my cup of tea. And then, secondly, I had this self realization that I wasn't smart enough to be able to contribute to that field of theoretical physics. And then I also like to be able to answer, so what? So I just thought, no, this is not for me. So that's why I started with geophysics. And I absolutely loved it because, you can actually connect the science to something practical, something deliverable, like density. You take gravity, you translate it to density, and then that density can be translated into a piece of rock. You can pick it up and you can feel it. So I really like that aspect.
love that.
And then when I started to work as a geophysicist, I discovered one more thing. And that is, you'll probably hear that from lot many geologists and geophysicists, that we got to go to places,
Mm.
many different places, beautiful places, and some places only a handful of people will ever see.
Yeah.
So I've been to some amazing places where you go there and you feel the energy and the warmth from the nature, and you get connected to nature in a way that in any other ways as a tourist is never going to be possible. So here I am still doing geophysics after 28 years.
Oh my gosh, that is such a cool story. And yeah, it sounds like you have gone far and wide. You've worked in India, you've worked in Australia. I think you've worked, yeah, when we caught up, it seems like you'd seen some amazing stuff. I'm very curious what some of your favorite highlights are so far.
Um, if I think back, favorite highlights, I'll talk about two, and a bit later I'll go through my career journey a bit more detail with some photos. But one is implementing new technologies. And in this one, I wanted to talk about this fast grade tool we implemented in the grade control. I'll talk about the story a bit detail later, but what I wanted to talk about now is that lessons I have learned. And that is for every technology implementation you do. One is that, the first lesson was that your technology can be best in the class, but if you don't lead the change well, it will not be successful. That constant stakeholder engagement and the communication is really, really important. So that was the first lesson. And the second one is about putting the system and processes in place so that it is sustainable. And often we don't put a lot of emphasis because from the beginning that you want to trial this tool, you have to have that vision, how it's going to work in day-to-day business. And you do have to put a lot of effort on that. And the third one, and the most important one, is that you've got to have dedicated people who believe in that technology, who believe in that use case, and you need to have that sponsor who will support you throughout the whole journey. And it can take years and years and years. And you need a lot of resilience and tenacity. And that's something I thought was that realization that a good technology, we can make it or break it. So that was a bit of a highlight. I did had the privilege to be part of many technology development and implementation. And the other highlight will be always people. And then in our environment, in any industry, people are the best resources we have. And that the realization of the power of collaboration, and especially someone like me who started as a technical specialist, a sole contributor. But then the realization that, if you have a big idea, you actually need a lot of people to push it. Yourself can only push a small idea. So, that true power of collaboration, I had the opportunity to work in many projects where that comes really, really apparent, that cross across different discipline, that cross discipline collaboration that is so important. And those learnings that comes with different projects you work on. So I would say those are highlights.
I love that. There's some great tips in there. So you've figured it all out by the sounds of it. It's awesome. Yeah. And I'm really curious, what pet rock you've brought along for us today.
Well, I am more a book and a data person than rock person, but
Yeah.
I do have a few special rocks in my bookcases. I brought one. Can you see it?
Yes.
I'm sorry, I'm not prepared to lick the rock because if I
We
look better,
don't lick rocks, no.
I used to lick rocks, but I haven't done it for a while. So, but anyway, so that's a piece of a core. It's a half core, and that's from IOCG target we had. It called King George. I could see SBON online, and SBON would remember this. This is we flew a airborne gravity gradiometer survey there. It is just off the Stuart Shelf, and the Munta Wallaroo copper gold mining field. So we did this survey. We had this great target, great gravity and mag anomaly. We had good geological model. We thought we might have a big IOCG deposit there. And I did the interpretation, I did the modeling, and I actually wrote a paper and presented at the ACG. I was young, optimist, and I was very lucky because I presented the paper before they drilled the target. So I probably had a lot of hope when I presented, but eventually it was drilled. We drilled one hole into that is about 20, 30 meters below water. Unfortunately, it's didn't turn out to be what we thought. There are traces of pyrite and chalcopyrite here. You probably won't be able to see it um, well, but I did have a lesson from that. That every time I look at this core, I remind myself that sometimes you might not get to where you exactly plan to be, but the journey is important and the lessons you learn along the journey, that's important. So even though it wasn't a big IOCG find, but I learned how to go about doing exploration, and that was an important lesson. Um, I remember those highs and lows, standing and talking about the drilling we are going to be doing, and then the disappointment, but then understanding that that's okay.
That is brilliant. Oh, you've got
So that's my pet rock.
I love that pet rock. You've got so many awesome pearls of wisdom for us today. So thank you. I'm very excited to have you on. So thank you for taking this time. Yeah, if you want to share your screen and we'll get stuck into it.
Before I start, that's the disclaimer. It contains some forward-looking statements. I'll give you a second to go through that. Uh, So I thought I'll start with a bit about my career journey to date. I started my career with BHP in 1997 as a graduate geophysicist. And BHP at that time had an office, exploration office in Udaipur. And Udaipur is in Western India, in Rajasthan. And we were exploring for lead zinc there. And later we kind of expanded to iron oxide, copper, gold as well. And I spent a lot of time doing field work in Rajasthan. And you can see in that picture, the top left corner, um, the person who's holding a magnetometer is me. And I'm surrounded by all these Rajasthani teenagers and women. I used to have a lot of people follow me around because it was a very unusual sight, actually. A young woman with a strange tool working around. But it was fun. So we flew about 16,000 square kilometer airborne EM and MAG in that area. It was a very systematic exploration program. We did the regional data analysis, we did some target generation, and then we actually went and ground truthed all the targets, the priority ones we generated. We did ground geophysics, we did MAG, and a lot of frequency domain EM. And we used to have this system called MaxMean. It's a Canadian system, and it had 400-meter and 200-meter coils. And at the end of the day, we have to wrap the coils up. And again, that attracted a lot of audience as well. And we did a lot of soil sampling and geological mapping. And at the end, we had a handful of drilling targets, which we eventually drilled. Again, it was a technical success. We didn't really find a big lead zinc deposit in that part of the world. But anyway, that's a lot of lessons I have learned. I learned how to systematically do minerals exploration, greenfield exploration. Amazing. And then I moved to Melbourne in 2000 to work in the BHP research in the minerals technology division. And that's when I worked with SBM. And I must say that when I moved to that office, I was quite intimidated. They were the smartest bunch of people I have actually ever met. Really, really switch on scientists in that group. And so what they were doing, they were building this airborne gravity gradiometer system there. It was a technology that we took it from US Navy, It was in submarine, and they were trying to put that in an aircraft. And the vision is that ground gravity, those who have collected ground gravity survey, you'll know how long does it take. If we get 80 station a day, it's a good day. So in an airborne platform, we can cover way more ground in days. And this is another big story, actually. You should invite Dr. Mark Dransfield to hear about that story. It's an incredible story about how we took a concept and then build a prototype and then eventually put it into the practice. I spent once it moved to prototype, from prototype to business as usual, I spend a lot of time again looking at how we can integrate it as a geological tool and target generation tool in the exploration workflow. Did a lot of technical marketing, and eventually moved back to exploration again, and mostly work for copper and diamond at that stage. Again, incredible experience with that Falcon team. And that figure there, just where you can see King George Falcon AGG, and that's the target we drilled. That's a vertical gravity over that King George target. And in the exploration, it was really fun. But 2003, I had a bit of change in my personal life. I became a mother. And I continued with exploration for some time, but it was a bit difficult. It was really fun exploring for kimberlites in Botswana. We are using gravity and mag to look through the Karoo basalts there, but it wasn't sustainable with a baby at home. So I had a bit of a pivot in my career. I decided to join BHP's Western Australian Iron Ore division. And when I was moving, one of my colleagues actually said that, do you really want to go to iron ore? They are, they don't need geophysicists. They've been mining for 40 years. And it's really easy. They just dig up the dirt and put it on a train. But when I arrived in iron ore, I realized that, oh, he couldn't have been any further away from reality. So I had lots of fun. Next 16 years I spent in iron ore. And you can see that mag image of Pilbara, one of my favorite magnetic image there, and some well and data there. And I had lots of fun. I have spent time putting technical standards, putting QA/QC processes, and did a lot of brownfield target generation, resource range analysis, and a lot of geophysical application over the whole mining value chain. And then slowly, I started to lead other technical teams as well, not just geophysicists, but geochemists, geometallurgists, metallurgists, data scientists, data management personnel, technical geologists, structural geologists. It was really fun, and we worked a lot of time with the site personnel as well, mine geologists, production processing engineers. And that's the period when I started to grow really interested in the application of geophysics in mining, and realized that there is a huge potential there. I worked with Andrew during that period as well. So lovely to see you, Andrew. And last year, I moved to this new global role with Resource Center of Excellence, and really excited about this opportunity because now I get to influence the whole of BHP across different assets and exploration, and not just iron ore. And I hope I can work with our industry colleagues as well to make some changes there as well. So today, I'm going to talk about geophysics in mining value chain. As I said, I spent 10 years of my career in exploration. that was exciting. So when I came to an operating asset, I didn't really know what to expect. Once an exploration target is deemed economically feasible, it triggers a whole lot of intense activities before developing and operating a mine. It's a whole new adventure. And the statistics says it takes about 16 years to make a greenfield discovery into a mine. But I was lucky in the sense that when I joined iron ore division, it was the time when whole iron ore industry was growing at an exponential rate. So in my 16 years with BHP Iron Ore, I have been involved in the development of two new mining hubs. And that's the point. And during that process, I realized that geophysics in general is vastly underutilized and it holds a huge potential across the entire mining value chain um, when we align with the key value drivers. So today, I wanted to talk about potential of geophysics in the mining value chain from a very personal perspective, actually. So I have chosen some case studies that I spent quite a lot of time, and I quite enjoyed doing those. Um, and I'll be using the words mining value chain and a key value driver a few times today. So I thought let's start with what is a mining value chain. Um, I'm actually not exactly sure who came up first with the term mining value chain. So I did search up in the Google, and the first thing you kind of see is a paper from McKinsey, and it says, I think pit mining to pit or something, but it talks about this whole mining value chain. But I think that the term value chain, it's quite relatively new, and it was introduced by Michael Porter in 1985 in his book called Competitive Advantage, Creating and Sustaining Superior Performance. So our value chain can be defined as a series of interconnected activities that add value to the outcome. I think that part, that interconnected and series, is important. And Porter divided these activities into two buckets: primary activities, those that directly involved in production and delivering the product, and support activities. And those are the enabling activities that help to improve the efficiency and effectiveness of the primary products. So the idea is that by analyzing each step, a company can identify ways to gain competitive advantage, either by reducing cost or improving productivity, enhancing safety or use of innovation, and so on. That diagram there is a typical mining value chain, um, showing the primary activities only. And some routine task, I have put it under each activities. And the list is not at all exhaustive. We can actually go on hours and hours just talking about this little piece. Um, and until you are in a mine, you actually don't understand how many things needed to be done before we dig the material up and it reaches our customers. So the important takeaway here is that each stage has some unique risk and decision pathways. Enormous amount of data and knowledge is gathered and generated across the value chain to support the decisions pathways, and that leads to a smooth operation. Now let's look at the key value drivers. And again, important thing to remember about data, and that's something I keep reminding myself all the time, is that the data must be turned into information and knowledge. And with this information or knowledge, we need to be able to make decisions or reduce risk or change our understanding. If it changes nothing, there is actually no value for this information. So the mining value chain, as you saw, has got series of activities, but we turn into massive inefficiencies if we conduct these activities in silo. And that's a lesson I have learned really well. So the key value driver approach is a way to integrate all these activities to understand which levers to push to enhance the value across each step, but at the same time, not to push the bottleneck to another step. So understanding that what are the key value drivers at each step are and how they are connected to the value drivers at another step are actually really important. And if we do it well, we can uplift the value across the whole mining value chain. So the key value drivers are those tasks that directly influence the performance and are controllable. And the beauty is that they are controllable and we have the lever to increase the value. So the decisions, again, we take or the decisions we don't take influence the key value drivers. To make the better decisions, we need data. So it is really important to understand the key value drivers to ensure that the right data is collected at the right time. And this is just an example of a key value driver tree. For each part of the mining value chain, we can generate a value driver tree. And how well we integrate is the key to success. For example, here is a value driver tree for a mining operation. If we look at profit, it's a function of the revenue generated and the operating cost. And if we look at the revenue, we have got exchange rate, commodity price, and production, which influence the revenue. But we don't have any control over commodity price. We don't have any influence over exchange rate, but we have a lot of control over the production or the shipped throughput rate. So if we now break down the production, some of the key value drivers are tons and grade. There are a lot more, but I'm just talking about those two for now. So let's look at tons then. So the geology model, mine design, subsequent extraction process, all these things is going to affect the tons that we produce. And now we can go down each branch again and identify activities that affect the operational outcome. This approach provides a very structured way to analyze the drivers that impact performance the most and help prioritize activities that directly contribute to the business goals. Well, you must be wondering, where is geophysics in this? It is coming. I have elaborated this a little bit because as a geoscientist or as a geophysicist, I did struggle when I was younger to articulate the value. I still do. I still struggle and I'm trying ways to find how I can better articulate the value. Because we need to be able to link our wonderful work to a language which is understood by decision makers. So we use a lot of geophysics in the exploration phase. Minex consulting team presented at PDAC in 2020 on the challenges and opportunities for geophysics for making discoveries undercover. And they have carried out some very detailed analysis of the discovery of about 4,500 at project and prospect scale. They excluded the bulk commodities. And it was highlighted that since 1950, use of geophysics as a primary method accounted for about 10% of the discoveries at project scale, use of geophysics. And this increased to 22% in the prospect scale. And remember that this statistics is only for the reported case. And so if we do a search, we can see a lot of geophysical case studies for greenfield exploration. But if you go and search for brownfield and near mine, there are less examples available out there. We talk a lot about the ore body, but if you go through the key value drivers in a mining value chain, you quickly realize that there is a way more than the ore body, the grade, and the tonnage. There is material handleability, there is productive movement, geotech hazards, ESG consideration, water management, tailings, and so on. So there is a lot of physical property information we require, and a huge amount of data is actually gathered across the mining value chain, some intentionally and some as a byproduct. For example, all our drill holes have got measure while drilling, and from that we can get physical property as well. So if you look across the mining value chain, there are numerous physical, chemical, and mineralogical properties that we measure repeatedly and at different scales. And there are more that we should be collecting, while and which are linked to the key value drivers. And geophysics measure just that. All these physical properties that you see on the screen, geophysics actually measure that. So in the next few slides, we'll look at a few case studies looking at the use of geophysics with the lens of key value drivers. So let's start with density. So geophysics for, I call it mine productivity. So density is a very important physical parameter. I'm a big fan of gravity, and that's the reason I get quite attracted to density as well. It is directly linked to tonnage, and it's also important to know the density of the waste rock because it provides the data to plan efficiently how many equipments we need to required to move that material and execute the mine plan efficiently. For iron ore and coal, density logging is a part of standard logging data collection. And it is a very simple geophysical tool. And I really like that simplicity there. And there is a radioactive source that emits gamma rays into the formation. The gamma rays interact with the electrons in the rock. Denser the material, more scattering will occur, and less gamma rays will come back to the detector. Total count of gamma rays in the detector can be turned into a bulk density measurement using calibration. Perhaps not as simple as I take it, but there are a few intricacies there. Those who deal with density data will understand that. And for coal, apart from tonnage, it also provides quite useful information about coal quality. And density logs are also used to locate coal in a borehole because density show up as low density. Coal show up as low density. The traditional method of collecting density measurement is from core. A lot of people still think that core density is superior quality to wireline density, and they somewhat lack the confidence in density logs. However, this is not the case. With routine calibration and QA/QC processes that checks the repeatability and reproducibility of those tools, wireline density is a very consistent and effective way of collecting good quality in situ bulk density data. And accurate density measurement over the economic and the non-economic material enables efficient production and better reconciliation. Those who does reconciliation, they will feel the pain if we don't have good density data in our resource models. And density is a measurement that is measured actually each step from resource definition hole to pit to stockpile and to the port. So there is the geophysics in the resource estimation process, very important part in the mining value chain. The next one I wanted to talk about quality. So quality, if you remember that key value drivers, quality is actually another key value driver for mining value chain. How do we control quality? How do we ensure that we deliver a customer the quality we promise? So one of the levers of maintaining quality is our grade control. That kind of determines the destination of the material and allows to control the grade variability. A common method of grade control is blast hole sampling. It is a manual sampling method from a drill hole that is drilled for the purpose of putting detonator on the ground to blast the material. Usually, a person takes a shovel and collect the samples from the cones around the blast hole. You can see the schematic diagram on the left side there. There's always an approximation of the depth from where the material has come from the height of the cone usually. An average 3 to 5 kilo of samples are collected in bags at required interval, and then they were sent off to the laboratory for analysis. And some operations sometimes take a bag for the entire hole, and it takes about 48 to 72 hours at least to get the results back. So the quality of the sample from blast hole is not optimal, and it is impossible to know the location where the sample is coming from. And also, depending on the sampler, from where he decides to pick up his sample, it might not be representative at all. So if we can reduce the sampling error, we can obtain much better ore and waste delineation and reduce the ore dilation. So it is a very powerful step in the mining value chain. So with that in mind, we sought to use in situ measurement because that will remove that uncertainty related to the sampling. So in this instance, we have used a fast grade tool. This tool routinely assays iron, alumina, silica, and phos, and we estimate or infer the loss on ignition. In addition, the tool can also measure copper, nickel, titanium, manganese, magnesium, calcium, sulfur, sodium, as well as hydrogen, oxygen, chlorine, and carbon with varying degree of accuracy. The sampling resolution is about 10 to 20 centimeter, depending on the speed of logging. This is considerably higher than 2-3 meter sampling, conventional sampling interval in iron ore. And the depth of investigation is approximately 30 to 50 centimeter around the hole. Again, that depends on the condition of the hole and the hole diameter and a few other things. A little bit about the tool. When I was talking about career highlights, I said that I would tell the story a little bit more detail. It's actually a great story of innovation, collaboration, and successful implementation of a new technology. So around 2005, CSIRO did a trial of their tool called Cyrolog to map sulfur in our Mount Wellbeck mine. So what the results highlighted that we can definitely measure sulfur, but it can be potentially useful to map iron. And we really liked the idea. But the problem was that we did not really want to put a chemical source in our pit. So later we approached CSIRO to build us an in situ chemical assaying tool without a chemical source. So around 2009, BHP, in collaboration with CSIRO and a French company called Southern, embarked on this journey of developing a neutron activation tool with a switchable neutron source. The tool is based on pulse, fast, and thermal neutron analysis for measuring in situ elemental concentration. So when we activate the neutron source, um, neutrons are emitted by the generator. They penetrate the surrounding rocks. As they penetrate the rocks, different interaction takes place, such as inelastic collision or thermal neutron capture. And as a result, characteristic gamma rays are emitted. The emitted gamma rays are measured by the detector. Each element produces a set of characterizing energies, and the amplitude of the emitted spectra is proportional to the amount of element present. Using calibration process, we then convert the spectra to assays. It is not very simple. There is a lot of sweat and blood goes into that, a lot of hard work, but in general, that's kind of is the concept. What we have done, we actually replaced the photo on the left-hand side with the photo on the right-hand side. In that photo on the left-hand side, a person is digging the blast hole samples with a shovel. And on the other side, a person is driving the vehicle. They don't have to come out of the vehicle. So they're inside the vehicle, and from one hole to another, they move, and the tool can position itself. You can actually see the tool sticking out at the back. It can position itself over the hole and collect the data and move on. So on the left side of the picture, there is a lot of manual handling work, and there is walking on the uneven ground and working in that extreme temperatures. With that tool, we remove those manual labor there, and also we replace the need for the samples to be sent to the lab. So at the same time, increase the sample turnaround time as well. So data is sent back in real time and can be processed instantaneously as well. So the sample availability time is also reduced from days to hours, and it reduced the demand on the on-site physical laboratories. And that journey did not happen in a day. It took years and years and years. Collaboration with a lot of people, external stakeholders, internal stakeholders, and then again, a lot of engagement between teams on site as well. But at the end, all the hard work paid off, and there is a lot of people involved there. A lot of my colleagues and people who used to work for BHP, a lot of contribution from a lot of people has gone into that. And the quality of the data, and you can see the figures from there. On the left-hand side graph, there is a vast improvement in iron, silica, and aluminum compared to other sample types. Here we have got traditional blast hole samples and RC drill for the grade control purpose. And you can see that the assays from the tool has considerably less error than both manual blast hole samples and RC grade control samples. And as expected, the blast hole samples has the highest error. They are the worst. And it's not surprising, because the blast holes were never designed to collect samples in the first place anyway. They were specifically designed to fill with explosive to blast the material. And if you look at the precision of the blast hole tools, the fast grade tools are quite high as well. And in that graph, we have plotted data from 3 different tools. And those tools are checked daily for repeatability and reproducibility. So this is a step change in the industry in a sense that it has allowed people to step up from being data gatherers to knowledge generators. Data can be collected by a machine and can be sent in real time to a geologist who is sitting in the office in a matter of minutes. And this also allows the possibility of near real time decision making. Um, and it is improving the quality of a grade control process. Uh, so, a great example how we have started with a vision, then we went on to develop the tool and brought in all the expertise that was available, collaborated with different people, and then finally put it in a day to day operation. The next one is slightly different. It is use of hyperspectral for geotechnical risk mitigation. Um, and this is an example of hyperspectral phase scanning. This work was done by my former teammate. And this mine phase scan captures a slope failure. And the failure is shown in that picture, in that white outline. That was captured with a normal SLR camera. Um, and below there is an average of all spectra captured on the slope failure is shown as well. The material on the failure surface is mostly ferric oxide and kaolinite. And the image here, um, the collapsed surface, which shows the relative clay content on the mine face. And you can see the failure surface is completely covered with clays. But most interestingly, you can see those thin layers of shale, which are kind of flat lying, are coming towards that side of that collapsed structure and turning into a tight syncline. Um, and this folding is outside of the zone that was disrupted by the failure. And every time I look at this image, I really get excited by that geometric detail that is captured by the mapping of that clay content in that infrared image, um, which you cannot really see on that visual color scan on the top image. So tracing the shale layers around the collapsed structure emphasizes that tight syncline. And combining the mine face map with the drill hole data, which is kind of behind that mine face, shows that that syncline is actually plunging towards the area where we have mined out, which is probably the likely to be the root cause of the collapse itself. Another great example where we can use geophysics to identify geotech hazards. The last one, example from tailing. This is something I have started to take a very keen interest lately when I started this new global role. And here are some facts which I've been learning myself in the last few months. Um, 13 billion tons of tailings are deposited per year. That is a lot. They are large engineered structures, and since 1915, there have been 257 TSF failing have occurred, displacing 250 million cubic meters of tailing, 5,000 square meter area destruction, more than 2,500 lives lost, and more than 300,000 people impacted. Either their homes destroyed or they had to relocate to another area. So, ensuring the safety of TSF is absolutely non negotiable. And Tailing Management Good Practice Guide specifies that good engineering practices, including a risk-informed approach throughout the life cycle, are needed to improve the safety of tailings facilities. So monitoring the changes and conditions in the subsurface of these facilities is critical to make decisions for their long-term stability and performance. Um, um, when I looked more into the tailings, they are quite heterogeneous system with various features at different scales due to depositional environment, composition of the tailing materials, stacking strategy, structural design, basement rock, and some other factors there. So to monitor the stability and characterizing the tailing material, it is important to understand the structure and the relevant material distribution within the tailing piles. And geophysics does have that advantage in the sense that it is not invasive, and also different geophysical techniques can be used to measure different physical properties. And then we can integrate those to produce a very comprehensive subsurface model. Geophysical methods such as the electromagnetic, electrical resistivity, and seismic can use to model different layers in tailing, general geometry, structures, geological layers, basement, fluid pathway, anomalous seepage. All these things can be mapped using geophysics. Importantly, it can also provide volumetric estimation, which is going to be hard using traditional drilling. And that image, I borrowed it from a paper. It shows an ERI section. You can see the low resistivity, high conductivity material in the dark purple and pink. And it shows the fluid movement over a more resistive basement rock or waste rock pile in that olive green rock. Um, I'm actually really looking forward to working with my colleagues at BHP and also some of my industry colleagues as well to build use cases for geophysics for tailings in risk management as well as characterization space in the near future. Um, So we are at the nearly end of our presentation today. We use geophysics quite extensively in the greenfield exploration, but in the mining value chain, the use of geophysics is still quite ad hoc. We have looked at a few case studies that show how geophysics data can influence the key value drivers. We didn't get to touch application for many other value drivers, perhaps a story for another day. So we drilled thousands and thousands of kilometers to define our resources. But imagine a world where we can make the transition from drill to define to drill to verify. Drill to define, that's what we do it now. How do we transition to drill to verify? And this is where geophysics can help. We also have the opportunity to build our knowledge on waste material. Traditionally, we lack a lot of knowledge there because we don't go and drill a lot in our waste material. So there is a huge unrealized potential to integrate geophysics into the mining value chain to proactively mitigate risk and enhance productivity when we look through the lens of key value drivers. And there are emerging technologies, new sensing technologies are coming. We have got machine learning and AI. So the future is really exciting. And I'm really looking forward to working with many people in the coming years to expand the use of geophysics as a routine tool across mining value chain. Um, Thank you for listening.
But this has been brilliant. Thank you so much. Yeah, it was wonderful having you on. I'm really glad we made this happen. So thank you for taking the time. It was really, really awesome hearing from you today.